So it's my pleasure to give an overview of the whole of the UK fusion sector. And that sector is moving from R&D excellence, so you can see on the left-hand side here JET, adding new technology facilities in the middle, and increasingly working with industry. As we deliver power plants, we firmly believe that that has to be led by the private sector. And so it's really important that we develop more and more of the partnership between the public and private sectors. Right at the heart of the UK government is an energy strategy, here announced by the Prime Minister from Cullum in March this year. And underneath that energy strategy sits a bespoke and specific fusion strategy. And that fusion strategy has two ambitious goals. The first is to demonstrate the commercial viability of fusion by actually building a prototype which produces net energy. And the second, as we've touched on the panel, is to establish an industry which is capable of building fusion components at scale. In order to meet that ambitious goal, we need a full, holistic approach, as the Minister said, to developing the ecosystem. So the way I see this in my head is like a tree. So initially you have to set the strong foundations for that sector to thrive, and that means investment in skills, it means investment in industry and clusters of industry. It means collaboration and partnerships with both international partners and industry partners. And it means new facilities to overcome challenges. So that brings a coordination to a concerted national endeavour. Once you have those conditions to thrive, you then need a strong trunk. And that trunk means that you need a breadth of skills across all of the challenges to deliver fusion, not just plasma physics, but then the robotics to maintain and engineer the plant, to build the plant, the materials that you build it from, how you manufacture and verify those materials, the tritium that you will fuel fusion with, and ultimately, because a lot of fusion power plant conditions are simply untestable, we need computing to be able to demonstrate to funders and regulators alike that we know what we're doing. And when you have those strong foundations and that core, you can then support a panoply of approaches. So lots of different approaches to power plants. Of course, in the UK, we're following a spherical tokamak path, but also we want to support ITER and the big tokamak paths, as well as many concepts being attacked by the private sector. So to give you an overview of the UK fusion sector, it's about 4,000 people now working in fusion directly. We've gone from a few hundred companies involved in fusion to now more than 4,000 companies involved in fusion. There are 32 UK universities involved in fusion. We set up a fusion cluster just a year ago. We thought we might get a few dozen companies sign up to that. We already have 205, and there are now 45 companies co-located at our Cullum Science Centre. As the Minister announced this morning, that will continue to be supported. A broad approach to holistic investment across the sector, new research facilities, a really important stimulation package for industry development, a new unprecedented investment in fusion skills, continuing to support our research base, and importantly supporting new and strengthened outward international collaborations. So I'm going to address a few things through the course of this talk. Firstly, the approaches that we have for addressing technical challenges in fusion. Then I'll talk a little bit about regulation, skills and places before finishing with a few words about our prototype power plant programme called STEP. So over the years, the UK has established a unique breadth from operating JET, which remains the largest magnetic confinement device in the world, and a number of spherical tokamaks. We've supplemented that with a strength in the underpinning technology for fusion, from materials research to how we might manufacture components and test them, to robotics, to tritium, storage and processing of tritium, and stitching that together with large advanced computing codes. And that then gives us the foundation to do power plant design, working with industry, increasingly working with industry, to develop the skills and the people that we need for that sector, and to think about technology transfer into fusion and also from fusion into other sectors. So I'm going to touch on each of these different examples over the next 10 slides. So starting with high-performance plasmas, we are delighted, in fact proud, to continue working with our European colleagues in Eurofusion over the last few years on JET, to now run 2 more deuterium-tritium campaigns. You'll hear later from Costanza the results from the deuterium-tritium campaign in 2021, where we set a new world record for the fusion energy released, a really important landmark result for our community. In and of itself, perhaps not that important, but it was what we predicted would happen. and that gives us great confidence as we move forward to ITER. Just 2 days ago, on Saturday, we ran the last deuterium-tritium shots in JET. We will now operate with deuterium for the rest of this year, but at the end of this year, we will transition from operations into the next phase of JET's life cycle. During the last 2 years, as testament to our commitment to working with companies, we have had companies embedded in learning about what it really means to operate with deuterium and tritium. Here you see secondees from Commonwealth Fusion Systems and Atkins Reales working with us on tritium operations. And we are now planning for the next phase of JET's life cycle. We feel a real responsibility on behalf of the global community to show that we can decommission JET not just reliably but rapidly and with minimum waste footprint. In fact, the tritium that's embedded in the machine is not waste, it's fuel. It's what we need. So we plan to disassemble inside out, taking apart the inside of the machine robotically, then detritiating solids and coolants, and indeed the Inconel, which makes up about 90% of the intermediate level waste, we have already shown that we can take out 80% of the tritium from that, and we hope to be able to do better in the future. So JET will now move into a decade of decommissioning, and we will learn a huge amount that the whole sector will benefit from. We also promote spherical tokamaks in the UK. We have completed the assembly of mast upgrade. That was a 7-year project where we were particularly aiming to address how we would extract heat from a compact design. Here you see modelling that we published 10 years ago of the reduction that we hoped we would achieve on heat flux incident on the wall by using our new approach to the diverter configuration. And when we turned the machine on in 2021, here were our early results. And these, I think, rather spectacular results show that you really can reduce the heat flux incident on the wall in a spherical tokamak by more than a factor of 10, in fact, more like 20 now. If you combine that approach to how we will exhaust the heat with high performance in the core, and here's some results from ST40, from Tokamak Energy, where they have now achieved 100 million degrees temperature in the core of a compact spherical tokamak. They are also now demonstrating with a full set of high temperature superconducting coils that you can handle the combined loads. So all the PF and TF coils, of course on a small scale, and looking at the combined loads between them, and then working with General Atomics to do fabrication at scale. So the pathway to spherical tokamaks is bright. Now turning to the underpinning technology, we have developed over the last few years a competence in materials research. We typically irradiate samples in test reactors like ANSTO in Australia or Haifa in the US. We then take that through our series of materials research facility. We can put small-scale samples into now one of 24 different shielded rooms. They're extracted robotically, put into instruments that the user can operate remotely, and that allows us to understand the damage on small-scale samples, which then informs better structural design. And then we can work with our industry partners to look at novel fabrication of those improved steels and improved structural materials at scale. And so we're doing that full loop and then back into irradiation for testing. But that's only looking at small-scale material samples. We also care about the brazes and the welds and the dissimilar things on large-scale samples. We are building a magneto-thermohydraulic test facility where samples in the middle are about 1.7 meters tall. And they can contain all those dissimilar brazes and welds. We then apply a very large inductive heat, a 4 Tesla magnetic field, and then pulsed magnetic field up to 12 Tesla a second to simulate disruption events, all in a vacuum, all under high heat flux. So testing those combined loads that you get in fusion devices. We also care deeply about how we maintain devices. In fact, it has the biggest exponent on ultimately the cost of electricity to the consumer. So we set up a center called RACE, Remote Applications in Challenging Environments. We have a heritage in big robots, so large boom robots that you see in both of these movies, which can do dexterous things on a sub-millimeter scale, but also large payload, hundreds of kilos. We used to have one of these boom manipulators, we now have 2, and you can see that being commissioned in the bottom right with a bit of fun. And that is in preparation for decommissioning of the inside of JET. But as well as those large boom robots, we're also thinking about how you do all of the different robotic functions that you need in a power plant, which might be in the top left here, quadruped robots for inspection and detection. Also thinking about how you might control them using new, like haptic gloves from the gaming industry, bringing that into fusion. thinking about how you control very large loads in the top left, so components that might make up casks in ITER, right down to the nuts and bolts. How are you going to assemble them when you can't send people in to maintain the machine? And that whole thing then needs a control software which a user can use for many dissimilar robots. So we have been developing a sort of middle layer that sits between the control system of lots of dissimilar robots and the one user. And all of this we will need ultimately for power plants. Another thing we need for power plants is management of our tritium systems. So we have set up a new center called HEAT, which is all about how we store and process tritium. This will do storage on metal hydride beds of 100 grams of tritium, so something like between 5% and 10% scale of ITER. Then extraction into ice, injection into vacuum, combination with other gases, as will happen in a tokamak. Then separation of those gases and separation of isotopes into protium, deuterium, and tritium, and then detritiation of materials and coolants. And that will allow us to do full inventory management, which is super, super important for power plants. As I said at the start, there are many conditions in a power plant that, frankly, we cannot test until we get to a power plant. And this means we will need higher and higher fidelity models. Now, we are a long way from a digital twin of a fusion power plant, but we are starting on that journey. We do have digital twins in the top right of some of our engineered components, but ultimately, for a digital twin of the whole plant, you need to bring together engineering simulation, plasma simulations at higher fidelity, and material simulations. So we are working on higher fidelity plasma simulations, getting ready for exascale compute, which is now coming online, by developing algorithms and tools which really scale. And here you can see some simulations of plasma turbulence in that regard. We're also working on ab initio modeling for materials damage due to radiation effects. Again, improving that using surrogate models to make that go much faster. And we are beginning to couple engineering simulations with material simulations and doing coupling neutronics and FE that we would do at large scale with this sort of ab initio modeling that's typically done at micron scale and doing that over meter large components. And we will now need to bring that together with plasma simulation to have a full digital twin. That's a long road, but it's one that fusion needs to go on. Because we've set up this ecosystem which supports all different approaches to fusion, we're also seeing real progress in other approaches too. So for instance, First Light Fusion have recently demonstrated that they can achieve a spherical implosion despite only having a one-sided drive. And they've demonstrated fusion for the first time using this approach and are now thinking about the next step, aiming for a gain experiment at the design of their next facility called Machine 4. And equally general fusion, a magneto-target fusion approach where they have demonstrated a high-force symmetric collapse of their liquid lithium vortex cavity and now are continuing those compression tests as they move forward with their next phase of development. Equally, the government are investing in new lasers. So the Central Laser Facility will soon get a $100 million upgrade to a single 20 petawatt beam laser, the highest power laser in the world, which may not be directly applied to inertial confinement, but will teach us a lot about laser development that could be useful for IFE in the future. And finally, we have set up a fusion industry program. So far, we have supported 135 companies in that program, many of them new to fusion. And the aim of that program is to take technologies developed in other sectors and bring them to fusion. So say, we don't know how to do this. This is a challenge for the community. Let's throw it out to other industrial sectors. And on the left, you see just one example of this. This is a small company typically working in biogas and combined heat and power plants. And they took their isotopic sieve technology, brought it to fusion, using special membranes, in this place, graphene, to try to drive down the scale of isotopic separation, which at the moment we expect to be pretty expensive and pretty big in fusion. Conversely, the opposite is also true, where we take technologies, in this case, TAE Power Solutions, who have developed an energy management system for fusion, and then spun that out into other sectors. They have recently acquired 2 companies in the UK, Sprint Power and Eltrium, and are now applying that technology into power management, into electric vehicle charging technology, and also into energy storage. So we're seeing lots of spillovers from fusion into other sectors too. I'm going to say a few words about regulation, our approach to developing skilled people and places. On regulation, the UK government have gone through a 4.5-year journey now to think about how fusion should be regulated in the UK. That began by commissioning the Regulatory Horizons Council, a government body who look at new technology to market and how it should be regulated. They've recently done genomics and artificial intelligence, but the first thing they did was fusion. And they advocated for a proportionate pro-innovation approach to regulation. That led to a green paper, which is a consultation process in the government, ultimately a government position paper, and is now passing as primary legislation. We expect it to be written into law in the UK within about a month or so. That fusion will be regulated by our Environment Agency and our Health and Safety Executive, not our Office for Nuclear Regulation, so taking the same approach as sort of radiation sources in hospitals. And that will be a big step forward, that we have clarity about how fusion will be regulated, written into law. On skills, just a few years ago, we were doing about 10 apprentices a year. So these are school leavers that we were training as mechanical and electrical technicians. So we've scaled from 10, we now have 460 learners in school a few years later. They are going into one of 35 different organisations, and we will continue, the government are continuing to invest in this, to scale to about 1,000 a year within 3 years from now. So that's at technician level. We are also developing our PhD training provision. We have about 160 PhD students in the UK now, many of whom are trained by the Excellence Centre for Doctoral Training, led by the University of York, but with a consortium of universities. And one of the spin-outs from that Centre for Doctoral Training is the establishment of an industry school, where people who are new to fusion, they might be working in other energy projects and their company is getting involved in fusion, can go on a 2-week residential course to learn about the challenges of fusion and upskill themselves rapidly to address fusion challenges. This really is a national endeavour. You see that the cluster of companies working in fusion, those 205 I mentioned earlier, really are all over the UK. The universities are really all over the UK, and even the national lab, UKAEA, now has 4 sites. Our headquarters in Culham, but we have 2 sites in the northeast of England and 1 site in the far northwest of England too. At Culham, we are developing a campus which continues to grow. We have about 4,000 people on site, but that we expect to continue to rise. And we are building new facilities for tenants. In the bottom left, you see a new R&D facility which will open for one of our tenants in the middle of next year. We're building a new visitor entrance, new skills facilities, new conference facilities. We really want to benefit from the clustering of companies, and indeed 3 fusion companies, General Fusion, Tokamak Energy and First Light Fusion, have all announced that their next facility will be built at the Culham Centre. Finally, a few words on our ambitious prototype power plant programme called STEP. I put up this quotation from Walter Marshall, who was previously the chair of UKAEA and went on to be the chair of the Electricity Generating Board in the UK. He said, "There will come a time when we sustain a fusion reaction." Tick. Then there will come a time when we get as much energy from a fusion reactor as we put in, or we contend that that's also ticked. However, there'll never come a time when we get as much money out as we put in. And personally, I don't agree with this. But I think it's a really good challenge to the community that we must focus on this. It is not enough to have a product that works. You have to have a product that works and that people want to buy. And that means it has to come in at the right competitive cost. And so in fusion, we really do need to do more to think about how we're going to enter the market and at a cost that the consumer wants to buy. And that ultimately is the genesis of the spherical tokamak. The spherical tokamak is all about driving down scale and capital cost of the build. So we embarked on the back of the excellent results from Mast Upgrade that I showed you and NSD40 on a program called STEP, where we're aiming to produce net energy gain to minimise the capital cost approach for the power plant. And so far, the government have invested nearly $400 million into the concept design phase. That concept design phase finishes next year, at which point we had to mature the concept, we had to set up a regulatory framework that I told you about, we had to choose a site, and we had to establish a company for delivering STEP. Then we go into the detailed engineering design phase, which will be almost 4 times the budget required, into long lead procurement and into site development before the main construction happens over the 2030s, aiming to complete the plant by around 2040. We recognise that this is an audacious timescale, but at the same time it's slower than we'd like. So it is both too slow and too fast. And in terms of siting, we went through a volunteer nomination process. We had 15 nominations all over the UK, down selected to 5, and ultimately the government last year chose this site. Up until March this year, it was operating as a coal-fired station in the north of England. That is now, the decommissioning is now well underway, and the demolition of the thermal plant will start soon. But the site is huge. We could host multiple fusion power plants on this site, and it has loads of great assets. It has a train line for bringing in goods and people. It has a direct connection to our national grid. It has a 2 gigawatt abstraction license of water from the river. That river connects to the second largest port in the UK. So it really allows us to get going. And perhaps most importantly, it has a community who for decades have worked in power generation and are desperate for new power generating projects in their community. And we really are seeing a project here going from fossils to fusion. So it's very exciting. And finally, we said we had to set up a delivery body. So we've thought hard about this, and we are setting up a new company limited by shares, called UK Industrial Fusion Solutions. That will, in the first instance, be a subsidiary of UKAEA on behalf of the government. And the first thing that company will do is to bring on board 2 large partners, a whole plant engineering partner and a whole plant construction partner. Now, those actually probably won't be single companies. They'll be consortia in and of their own right to have the breadth of skills that are needed for this large project. And we hope to establish relationships with those partners which go on for decades. And this is a slightly different approach to maybe a public-private partnership that we're seeing in other countries. Here we're trying to bring very large tier ones who have experience of building big energy projects. That could be in nuclear, it could be in wind, it could be any type of energy, but big energy firms who actually have the balance sheets for projects like this. And that's what we're trying to achieve through the STEP programme. In fact, in some sense, it doesn't really matter what concept we're pursuing. What we're doing here is galvanising an industrial base, working together to have a platform that can deliver power plants, fusion power plants in the future. In some sense, it doesn't matter what concept. This is about catalysing that ecosystem. So I will finish there and strongly recommend that you go and see some of the many contributions from the UK fusion sector being presented here this week. And actually, it's delightful for me to see that it's not just national labs and universities, but also big companies and small companies and fusion companies all presenting contributions here this week. So thank you very much.